what we get. All right, so section 2.3 is the more algebraic way of solving limits, right? Before section 2.3, we just could like guess at what the limit would be, and I hate guessing. We could estimate what it would be, but now we're going to refine that a little bit more and say, okay, how can we actually calculate those? And we have all of these limit laws, right? The operation laws where the limit of the sum is the sum of the limits. The limit of the difference is the difference of the limits. If you have a constant, you can pull it out and multiply it out front. The limit of the product is the product of the limits. The limit of the quotient is the quotient of the limits, as long as the limit of g is non-zero. And then we had all of these rules, which really kind of beefs up our solving capabilities, especially this one right here. The limit as x goes to a of x is a. And why is that true? I didn't really talk about that in this class, but think about it as in terms of the line y equals x. Pretend that's going through the axis there. If you take any value, say 1, if it's the line y equals x, and that's the function, right? X, that's just the function, y equals x, or f of x is equal to x. If you look at 1, what's the y value? 1, right? The x value matches the y value. And I know at that place, but if I did that all leading up to it, it would be 1 as well, right? Well, if I just expand that to any number, does that work for any number in that line? Yeah. So you can generalize it to be a. If I say it's going to approach a, the output is a. So as long as the limit of the limit as x approaches a of x, it's always going to be equal to that value that you're trying to approach, a in this case. Okay. Now, we have all of these rules, and we started here, and we said, okay, now what we can say is if I apply the limits to all of these things, well, then it's just going to evaluate to be each little limit of each little piece, right? Okay. Then we said, well, if that's the case, then we can expand that to this whole substitution property. And this is a very, very, very convenient rule for us. If f is a polynomial or rational, and yes, we will expand that, but here's where we're at right now. If f is a polynomial or rational, and a is in the domain of f, for a polynomial, that's not a sticking point. For a rational, that is a sticking point. As long as a is in the domain of f, then the limit as x goes to a of f of x is equal to f of a, meaning all I need to do is take that a value and plug it into the function. If we have polynomial or rational, that is called the direct substitution property. Functions with the direct substitution property are called continuous at a. And again, we're going to study continuity in great depth in section 2.5. And then we had this problem where we could not do direct substitution. There was this sticking point of, okay, well, it's non-zero zero's in the denominator, right? If I'm trying to plug in. There's always ways you can manipulate it to get around it. I don't say always. There's usually ways that you can manipulate the function to get around the denominator being equal to 0. Okay, we did this one, correct?
Yes.
Right. All right. So note, in example 3, we were able to compute the limit by replacing the given function f of x is equal to x squared over x minus 1 by a simpler function with the same limit. This is kind of like the culmination of that problem. If f of x is equivalent to g of x, meaning if you can get two functions that are equal to one another, which we saw x squared minus 1 over x minus 1 was equal to x plus 1 as long as we canceled out the x minus 1. When x does not equal a, the limit as x goes to a of f of x is equal to the limit as x goes to a of g of x, provided that the limit exists in itself. Right? All that statement is saying is that if you can say two functions are equal, if you can reduce a function, then you can use that new function and find the limit there, provided that the limit exists. All right, so let's try to get weird with it. Let's do a piecewise function. Let's try to do some funky stuff and see if substitution exists here. Because we talked about polynomial, we talked about rational. Let's do a piecewise. Now think about the components of this piecewise. The components of this piecewise are linear and then a constant, right? It's just pi. It's not like a sine of pi or anything like that. or a sine of x, or whatever it may be, this is just literally pi. So it's just a constant. All right. Just gonna have my notes out so I don't screw anything up. Okay, so I want to find the limit as x goes to 1 of g of x. Okay, the limit of x goes to 1 of g of x. The limit, the limit as x goes to 1 of g of x. Well, what is g of x going to act like around 1? What is g of x going to act like around 1? What other function is it going to act like around 1? Is it going to act like x plus 1? I cannot do direct substitution here, because if I were to try to do direct substitution, it would give me pi, right? But it's going to act like x plus 1 around that value. At 0.9, it's going to be x plus 1. At 1.1, it's going to be x plus 1. So we can say that the limit as x goes to 1 of g of x is going to act like, and I should be a little bit more specific and say, the limit as x goes to 1 of x plus 1. See, that's what that last statement was saying. If you can replace a function with a new one, you can evaluate the limit at the same place, as long as it's happening around a, in this case 1. All right, so in this case, I can do direct substitution. 1 plus 1 is 2. So the limit as x goes to 1 of g of x is 2. So what we did there was we replaced this piecewise function with something that it was going to act like around that value. So you can use direct substitution, but you have to be a little tricky with it. You have to be a little particular, because you can't be looking at where it's happening. You have to be looking at what around where it's happening. All right, we have 3 plus h squared minus 9 all over h. It's going to start to look more and more like difference quotients. 3 plus h squared minus 9. Now, your first instinct may be, could I do direct substitution in this case? Like, as it sits right now, could I do direct substitution? No. So the rule to follow is that you try to manipulate it as much as possible before you throw in the towel, before you say, well, this can't be done by direct substitution, and we've got to use another method. And in that case, we'll learn what happens in that case, right? So we've got 3 plus h. Uh-oh, Miss Naples, come over. What's up?
Practice quizzing quiz for Algebra 1. Are we good to go?
Yes, those were good.
Thank you.
Yep. So we have, let's try to simplify this down. 3 plus h squared minus 9 over h. Well, I can simplify that by foiling the top left, right? 3 plus h squared. So that'll be 9 plus, we have 3h and 3h to make 6h plus h squared. Right, 9 plus 6h plus h squared was that 3 plus h foiled out. A trick to foiling binomials, if you haven't gotten there already, I know I taught this in Algebra 2, but we just kind of glaze over it and say you can always foil. Square the first, double the product, square the last. That's how you do those quickly. Square the first, 3 squared is 9. Double the product, 3 in h, 6 in h. And then square the last, h squared. So that'll save you some time if you can have that in your memory. Now, the nice thing about this here is that some things are going to cancel. Well, not some things, just something. It's going to cancel. Those 9s are going to cancel, leaving us with an h squared, I'll put it in standard form, over 6h, all divided by h. And what can happen with my h now? That can cancel as well, right? I'll factor out an h to get h plus 6 over h, and that will cancel, leaving just an h plus 6. So I have now created an equivalent equation that I can find the limit of. So I can replace the function, the limit as h goes to 0, of h plus 6. So I can manipulate it so that if the h gets out of the denominator, I can evaluate it because now I can say, well, the limit is just 6. 0 plus 6 is 6. So I can say that the full limit of this is 6. That makes sense? You can manipulate it to force it into being solvable, right? Now, this one may look familiar. Remember, we did this one in section 2.2. We looked at this one in section 2.2. This is that one that we thought was going to go to 0. But it didn't actually go to 0. It actually leveled out before it went to 0. Now, you may be thinking, man, is there any way to simplify this? Like the square root of t squared plus 9. Square root of t squared plus 9. Can I make that t plus 3? Can I do that? No, you can't do that. That would be nice. Heck yeah, that would be nice. But that doesn't work like that. You can't just square root that t squared plus 9 and make it t plus 3. Okay, so we got to do something a little tricky. I'm going to teach you a method that may work sometimes. This is when you have a square root in the numerator. You can actually, I don't know, I call this unrationalizing the denominator. You can actually put the square root back in the denominator, maybe to give it something else down there so that hopefully something may cancel. Now, when you rationalize the denominator, you multiply by the square root in the numerator and denominator. But if there's multiple terms, you'd have to multiply by like a conjugate, right? You have to multiply by the conjugate. Like, for example, if you had something like, I don't know, just making this up off the top of my head, x over x plus square root of 3, right? To get the radical out of the denominator, you would need to multiply by x minus radical 3, right? Multiply by the conjugate. And why do you do that? Because in that case, that's going to create a difference of squares, and the last terms will multiply together, and the inners and outers will cancel, leaving no radicals in the denominator anymore. So if I'm going to reverse that process, I need to multiply by the conjugate of the numerator. So this is a t squared plus 9 plus 3 over t squared plus 9, radical t squared plus 9 plus 3. We're kind of unrationalizing the denominator. Again, this is just kind of like another tool that you can use to throw at a problem to see if it might help. Does unrationalizing the denominator work every time? No. But you'll see here in this case, it does. All right, now you got to consider this as like two big parentheses, right? You got to FOIL that. Okay, first, the square root of t squared plus 9 times the square root of t squared plus 9. Doesn't that just get us t squared plus 9? Multiplying two square roots together just kind of takes off the radical. So t squared plus 9. And the reason we use a conjugate is because the inners and outers will cancel. Take a look at my inners and outers. My inners is a negative 3 radical t squared plus 9. My outers is a positive 3 radical t squared plus 9. Those will cancel because I've used the conjugate. And then I have my last. Negative 3 times positive 3. That's a negative 9. Hey, that looks convenient. Now, again, I'm going to have this here. However, what's the top going to reduce into? Just t squared, right? Eventually. That's just going to get us a t squared. Okay, now here, I'm not going to multiply that in. And you'll see why. Maybe you already see why. You see now? That t squared is going to cancel, leaving us with 1 over square root t squared plus 9 plus 3. Now, I hope we can evaluate the limit now. If we can't, If I plug in and it's still going to give me 0 on the bottom, well then shoot, we did all that for nothing. Not for nothing, just for the sake of doing math. For fun. Oh, not x going to 0, t going to 0, excuse me. The limit as t goes to 0 of this. So let's see if we can directly substitute. 1 over 0 squared plus 9 plus 3. Ooh, we are going to get a good number here. This is 0 squared plus 9 is 9. So the square root of 9 is 3 plus 3, 1/6. Anybody remember doing this problem a while ago? What did we get as our answer? 0.1, what is 1/6? 0.1, isn't it 0.16 repeating?
Yeah.
0.16 repeating. Let me show you. I believe it was here. Section 2.2. Let's see, let's bring that up real quick. But again, we did this algebraically. I've got to be honest, the plug and chug method might have been faster in this one. But for our purposes, I mean, it was all right. Wasn't too bad. Still coming up. But anyway, the plug and chug method kind of led us in the wrong direction, right? We thought it was going to go to 0 when in actuality it went to 1/6. We can see for our algebraic answer here, it was definitively 1/6. Yeah, here it is. Let me show you. Where was it? It was right. Oh, I thought it was over here. Where is it? Where'd you go? I think it was before that. Before this. Oh, there it was. Yeah. Okay. We see that if I run it down toward 0, it was actually going to give us that 0.16 repeating. Okay. So here we solved it plug and chug method. Here we solved it algebraically. I like the more algebraic route to take. The weird part about this is doing the multiplying by the conjugate of the numerator. That's weird. But again, just something new to use if you ever need it. All right. Some limits are best calculated by first using the left hand and then right hand limits. Okay, because we know left hand and right hand limits should be the same, correct? If the limit exists, then the left hand limit and the right hand limits should be the same. The following theorem is a reminder of what we discovered in section 2.2. It says that two-sided limits exist if and only if both of the one-sided limits exist and are equal. This is the same thing that we wrote down in the last section, right? That is the exact same thing, copy and pasted in. The limit as x approaches a of f of x is equal to L if and only if the limit of the function on the left side matches the limit on the function on the right side. When computing one-sided limits, we use the fact that the limit laws also hold for one-sided limits. So for example, this one. Show that the limit of x going to 0 of the absolute value function is 0. Algebraically show that. Okay. Now, I am not asking you to calculate a limit here. I'm actually asking you to kind of do a little proof. Show that the limit is equal to 0. Prove that the limit is equal to 0. It's an algebraic proof. One that we don't have to supply our reasonings for, just to show algebraic steps to it. Now, we know that, we've talked about this before, that the absolute value function could be written as a piecewise, right? The absolute value of x could be written as a piecewise if x is greater than 0 or if x is less than 0. And we just have to put the or equal to on one of them. All right. If x is greater than or equal to 0, what is the output? Like if I put in 2, what's the output? 2. If I put in 3, what's the output? 3. So if I plug in x, what's the output? X. So if x is greater than or equal to 0, then the output is just the same thing. If x is less than 0, okay, so if I plug in -1 into the absolute value, what happens? +1. If I plug in -2, what happens? +2. So we can say that this is -x if x is less than 0. Okay, well, let's calculate the two limits then. Let's calculate left-hand and right-hand limit. The limit as x goes to 0 from the left of the absolute value of x. Well, what's it going to act like? It's going to act like, if I'm going from the left, it's going to act like negative x, right? Is equivalent to the limit as x goes to 0 of negative x. Okay, well, that's just linear, isn't it? That's my substitution property. Okay, plug 0 in. The limit is 0. So I just showed that the limit on the left side of the absolute value of x is 0. Let's prove it from the right. The limit as x goes to 0 from the right of the absolute value of x. Well, let's replace it with a function that it's going to act like. So from the right side, it's just going to act like x. And we know, based on our limit laws, that the limit as x approaches a of x is just a. Right? That was this whole thing. So 0. Okay, what did we show? We just basically showed this theorem, didn't we? Okay, we can say that therefore the limit as x approaches 0 of the absolute value of x is 0. Kind of like the algebraic proof of that. Questions about that? Okay, let's do another one. Prove that this limit does not exist. Prove that this limit does not exist. Okay, now for this one, I'm going to use this same, I'm going to copy and paste this same piecewise. Whoa, no, don't do that. Okay. I'm going to copy, paste you on in. Nope. Paste, right click, paste. Okay. Because, well, why am I doing this? Well, I need to calculate left-hand and right-hand limits. To show that the limit does not exist, one of the ways to do so is to show that the limit from the left side does not match the limit from the right side. Let's see what's going to happen. Well, the limit as x goes to 0 from the left of the absolute value of x over x. Well, that's going to act like, what can I replace the absolute value of x with if I'm only looking at the left side of it? Negative x, right? So the limit as x goes to 0 negative of negative x over x. Well, what does that equal? What does that reduce to? What does negative x over x reduce to? Negative 1. Limit as x goes to 0 negative of negative 1. And the limit of a constant is the constant. So the limit on the left side of this thing is negative 1. What's wrong, Addison? I just reduced this fraction, negative x over x. Yeah. Because the x's will cancel, so negative 1 over 1. So the limit on the left side of this thing is negative 1. I bet the limit on the right side is positive 1. I bet. Limit as x goes to 0 positive of absolute value of x over x. Well, again, we can replace absolute value with this new definition for piecewise. Because again, it's going to act like it there. And look, yeah, the limit as x goes to 0 positive of 1 is 1. So we make a statement in the end, because this is a proof. I want to say, so therefore, the limit of x going to 0 negative of the absolute value of x over x does not equal the limit 0 positive of the absolute value of x over x. So which means that the limit, the full limit of absolute value of x over x does not exist. I don't know why I boxed that. That's not my final answer. The whole thing is my answer, isn't it? It's proof. Okay. So again, one way to prove that the limit does not exist is to show left side and show right side and show they don't match. Okay. All right, let's take a look here. Determine whether the limit as x approaches 4 exists. Determine if the limit as x approaches 4 exists. Let me first start by saying this. Does f of 4 exist? No. F of 4 does not exist. F 4 is not within the domain of this piecewise. 4 is not defined. Okay, but again, it doesn't matter what's happening around it. It matters what's happening near it, right? So like this one, I can't do direct substitution because it doesn't exist like that. It doesn't work like that. So now, the limit, we have to calculate both left-hand and right-hand limits to determine if it exists. The limit as x goes to 4 negative from the left side. Well, of f of x, what's it going to act like to the left of 4? It's going to act like 8 minus 2x. Well, that's just linear, right? Plug it in. Hi. So all I need to do is just plug that 4 in. Let's do that. 8 minus 2 times 4. Well, that's 8 minus 8, right? Or 0. Don't think because it's 0 that it doesn't exist. That's actually the value. So we know the limit on the left side is 0. Let's see what the limit is on the right side. The limit as x goes to 4 positively of f of x, well, it's going to act like, on the right side of 4, the square root of x minus 4. Now, let's directly substitute there. And we can do this because it is defined. If I plug in 4, it's going to give me a valid answer. I know I had only said polynomial and rational so far, but remember, polynomial is kind of like a square root. Powers are kind of like a square root. So we have the square root of 4 minus 4, which is the square root of 0, which is 0. Okay. We showed that the limit as x goes to 4 of f of x is 0. We showed that it does exist, and it's at 0. Questions about that? All right, let's keep going. The greatest, again, not every day that you get to learn a new function, folks. It's called the greatest integer function. Not a very common one, but hey, it's still a new function. It's called the greatest integer function. The greatest integer function is defined to be, and that's the symbol for it. It's kind of like a fancy looking bracket, like a bolded bracket. Right? This is, I kind of over exaggerated the size of those, but you get the idea. Like a double lined bracket. That's called the greatest integer function. That's the symbol for it. The greatest integer function is defined by it's equal to the largest integer that is less than or equal to x. The biggest integer less than or equal to x. So, for example, the greatest integer function of 4 is 4. The greatest integer function of 4.8 is 4. The greatest integer function of pi, okay, chop off the 0.14, is 3. The greatest integer of radical 2 is just 1 because it's 1.4 or something. Right? So it just kind of knocks it back down. The greatest integer of negative 1/2 is negative 1. Remember, I'm talking about value here. So if I'm at negative 1/2, the next one would be negative 1 down below it. Showed that the limit as x approaches 3 does not exist. Ooh, this is interesting. Okay, well, the limit as x goes to 3, I want to be very specific when I write this out. The limit as x goes to 3 negative and the limit as x goes to 3 positive, we want to show that those are not the same thing. Right? Well, what is the limit as x goes to 3 from the left side? If I had 2.8, what would it be? What would be the greatest integer less than or equal to 2.8? 2. What about 2.9? Still 2. What about 2.999? Still 2. What about 3 from the positive side? 3.1. 3. 3.11. 3.001. 3. And that process could continue. So we just showed right here that the limit as x approaches 3 from the left of the greatest integer function is not the same as the limit as x goes to 3 from the right of the greatest integer function. The greatest integer function looks kind of like piecewise-y in its graph. Let me actually show you what it looks like here. Yeah, there's no way we're going to get to the end of today's notes, so I'll stall a little bit for you guys. Greatest integer function. This is the graph of the greatest integer function. It's kind of like a step graph. Okay? Basically saying that as soon as I take the x value leading up to it, well, it's going to jump to the next one, right? So if the x value is 0.5, it's jumping back to 0. If it's 1.5, it's jumping back to 1. And then on so forth, it's going to just jump up successively. It's not going to lead up. It's just going to jump up. That's the greatest integer function. And we can kind of see it from here looking at the limits. You know, if I want to, maybe I'm looking at 3, 1, 2, 3. The limit from the left side is 2, but the limit from the right side is 3. It's not continuous. It does not connect with one another. So therefore, the limit does not exist. It jumps in there. Okay. Let me see what else we got. Okay, this is a good stopping place. We'll end a little bit early today. I want to end a little bit early because I did not get nearly as far with my seventh period as I did with you guys yesterday. So I got a couple more examples to go over with them. So this is a good stopping point. So that means